This is GATE 2011 question number 5, which states that in a first order phase transition, at the transition temperature, specific heat of the system. So these are the following options which are there. So we have to see that what happens to the specific heat of the system at the transition temperature during the first order phase transition. So for that, let us come to the solution. So we have seen that this is the solution. In the first order phase transition, the specific Gibbs free energy is continuous. This is known to us that specific Gibbs free energy is continuous for first order phase transition. Now dg, generally we write dg, the change in the Gibbs free energy or specific Gibbs free energy here, is vdp minus sdt, where dg is the specific the change in the specific Gibbs free energy, v is the specific volume, and s is the entropy. So this is how we write the thermodynamic potential, the Gibbs free energy, as this kind of a term. Now if we just put the pressure to be constant, so this goes 0, vdp becomes 0. So what we get is dg is equal to minus sdt. So what does it represents? That this specific entropy, this is specific entropy is nothing but the derivative, the first order derivative of temperature with respect to at constant pressure. So delta G by delta T with a negative sign at constant pressure. So in general, what happens is that if you just plot G versus T from this particular thing only or this particular thing only, there is a clear relation that G is actually related with temperature like this. Okay, so this is suppose phase 1, this is suppose phase 2, and because of the difference in the phases, the entropies are different, the slopes are different. So this is a kind of a, suppose that this is a kind of a behavior which is seen in a system. So what happens is that its first order derivative, which is the specific entropy, which is minus delta G by delta T, first order derivative of the Gibbs free energy with respect to temperature at constant pressure, which will result into some kind of a discontinuity. Why there will be discontinuity? Because there is a change in slope at the transition point that results into the sharpness in the curve. Although it is continuous across the first phase and the second phase, the G is continuous, but there is a sharpness, there is a change in the slope, across the phase transition point. So when there is a change in slope across the phase transition point, you can find out that any function which has a change in slope, you can find that its first order derivative will be discontinuous at that point. So at transition point, we have found out that there is a sharpness, there is a change in the slope, hence we get a discontinuity in the entropy at this transition point. And of course, in the first phase it is lower, in the second phase it is higher, as you can see that the slope here is stronger as compared to this in the negative sense. Now specific heat capacity at constant pressure, Cp, can be derived from this particular expression. This is nothing but the first law of thermodynamics. This is also first law. So in general we write Tds is equal to Cv dt plus Pdv. This is the general first law of thermodynamics. Here we use Pv is equal to RT. So Pdv plus Vdp is equal RdT. So if you just put in this particular equation, we get Cv dt plus Pdv can be written as RdT minus Vdp. Now Cv plus R is nothing but Cp dt minus Vdp. Now for the specific case, that is if all this entropy, temperature and all these things are specific, then we can write clearly that it is T into ds Cp, specific heat capacity at constant pressure, dt minus Vdp. This is the first law of thermodynamics in another form. Now Cp at constant pressure, this should be 0. Cp can be written as T delta S by delta T at constant pressure. What we can see is that it is the first order derivative of the specific entropy, or what does it represent is that it is the second order derivative of this G, the Gibbs free energy. So now we have seen that in the first order derivative there is a discontinuity. So any function, any random function fx with function x at a particular point, suppose this x dash, at this point you can see that there is a finite amount of discontinuity, which can be seen over here also. There is a finite amount of discontinuity at transition point from one phase to another phase. So whenever there is any function, any arbitrary function having at a particular point, having a finite amount of discontinuity, then you can see that if you take its derivative, what will happen? The dy is nothing but c. The dy is nothing, so dy by dx. So dy is nothing but c. But what about dx? It tends to almost 0. So if it tends to 0, this entire slope will tend to diverge. It becomes tending to infinity. So c by delta x at delta x tending to 0 because it's only one point. So that tends to infinity. Hence, Cp will therefore definitely diverge at the transition point. Why? Because at the transition point, the entropy is having a discontinuity. So if you take another derivative of this, that will result into some divergence. And we can see that Cp, this is the first order transition of the Cp, and you can see that at transition point, you will find the entire graph, the Cp will tend to diverge. It will tend to infinity. So it will have a divergence point at the transition point between the two phases 1 and 2. So B is the correct option for this particular question. So if you come back to the question, you can see that the specific heat of the system, it diverges and its entropy remains the same. Well, no, because entropy is having a finite amount of discontinuity. So B is the correct option. It diverges, specific heat diverges, and its entropy has a finite discontinuity. Why? Because G, as you have seen, that there is a change in slope that result into sharpness, a kind of a sharpness. There is a change in slope at the transition point that is actually having, that is resulting into, if you take a derivative of that, it results into finite amount of discontinuity. So other options are incorrect. Remains unchanged. No. It is diverging, we have seen that, and has finite discontinuity. No, the specific heat of the system actually diverges at the transition point. So B is the correct option for this particular question. Thank you.